I'm going to talk a little bit more about WhizzML workflows, and in particular, we're going to get into WhizzML workflows that are sort of realistic, real-world workflows for machine learning. So in the last session, I talked a little bit about the language in general, as well as what code looks like in the language, and some various simple things you could do in the language, rather than kind of get into realistic real-world things. And now we're going to get into that latter bit where we actually use the language, what we used in what we defined in the last session, to do some more realistic heavy lifting for machine learning. And so with that, we'll start with a little introduction, and then we'll talk a little bit about advanced workflows in the machine learning world and why we might want to do those with BigML. And then we'll get down into the nitty-gritty. We'll do a WhizzML implementation of a kind of a fairly simple machine learning workflow called best first feature selection. After that, I'll go through a few more workflows, just kind of sketch solutions. We'll do another kind of semi-deep dive into a workflow called stacked generalization. And then we'll also take a look at a piece of a very complex workflow that we have implemented called gradient boosting. And then we'll wrap up. So from the previous two sessions, what do we know about WhizzML? First of all, it's a complete programming language, complete in the sense that it's Turing complete. So you can write any program you can write in any other programming language. You can also write that in WhizzML. The important kind of distinguishing factor about WhizzML is that machine learning operations in WhizzML are first class. So you don't need to import libraries or do any sort of complicated configuration. You immediately have a whole bunch of machine learning algorithms at your fingertips as soon as you start writing WhizzML. And then even more importantly, those operations, those machine learning operations that I just mentioned, are performed in BigML's backend. So you write your code. Perhaps with all these machine learning operations as part of the code, and then BigML takes those into its own backend. It does all of the API requests for you, so you don't have to set up and tear down connections. You don't even have to have network access for the duration of the script, because it's all running inside the backend. All the API requests are performed within the backend. And what that means is you get scale essentially for free. So if you're working with a very large data set that maybe doesn't fit into memory on your machine, or requires you to go off to disk a lot to read the data set and so on and so forth, all of those details are taken care of for you, because on BigML's backend we've done all that work to scale our backend to deal with gigabytes of data, and so when you're executing your WhizzML script on BigML's backend, you get all that scale for free, all access to all our machines, all the cores on those machines, and so on and so forth. And finally, we've kind of worked hard to make everything composable. So you have functions as first-class objects in WhizzML. WhizzML is a functional language, and so defining functions works even more nicely than in other languages. You can compose those functions into libraries that you can share with others, as we mentioned last time, and we'll see an example of a library in this set of slides. And then finally, on the web interface, I believe in the first talk, they showed how you can take the web interface and actually link a script to your custom web interface, so that when you go into the UI, when you are interacting with BigML, your user can have a shortcut to that script sitting on a particular menu where you might use that script a lot. So everything in the language can be kind of composed upwards and made into new things and reconfigured differently, so that you can kind of customize the tool to your machine learning needs. So what can we do with it? So a couple of the things that we've seen that WhizzML is useful for: model selection tasks. So that's a kind of common machine learning workflow that you do, where you split your data set into a bunch of training and test sets, and you train on the training data and you test on the testing data, and you use that to estimate the performance you're going to get out of sample when you deploy your model in the real world. Obviously, if you're doing something like n-fold cross-validation, where you're doing n splits of the data into training and test data, that's going to be something that's hard to do through the web UI. It's going to involve a lot of clicking and a lot of waiting for data sets to be made, and so on and so forth. All of that can be automated in WhizzML without too much work. In addition, you can compare different types of models. We saw in the last talk a simple script called Modeler Ensemble that would decide whether or not it was best to learn a single model over your data or a forest of tree models. And so that's something that, again, is trivial to do with WhizzML. You can use the language to create all your models, to do all your evaluations, and then to compare those evaluations against one another. The other thing that we kind of touched on in the last talk was how nice it is to automate drudgery in WhizzML. So if you do a lot of model retraining, or you have a specific workflow where you split the data into a specific train and test set, maybe you always use 20% for testing, you always use 80% for training. So instead of having to go through, when you upload new data to the system, instead of having to go through and create the data set, then create the split for the data set, then create the model, then create the evaluation, you can write a quick WhizzML script that will do all that in one click for you, if that's something you do a lot. So those kind of tasks that are laborious in the UI can be made automatic with WhizzML. And then, again, exported back to the UI so you have a one-click ability to execute that script. Also, something a lot of people do in the UI and in machine learning in general is to do some kind of standard dataset transformations. So we have flatline, this language for dataset transformation, which enables you to generate certain features from some other features. A really common example is delta features, where an important feature in your data might be the difference between one feature and another feature in the same instance. And those sorts of standard things that if you have a particular data source that you always transform in a standard way, getting rid of certain features, composing certain features, you can standardize all those sorts of transformations and data cleaning operations in WhizzML so that you don't have to, again, laboriously click through each bit of the UI to do those things. Okay, so those are sort of awfully simple use cases. And now, because this is the advanced tutorial session, we're going to get into what else can we do with WhizzML. Maybe some things that are a little closer to actual machine learning workflows, non-trivial algorithms that people have developed, meta algorithms for machine learning. So let's talk a little bit about some of those. Upshot of this talk, if you want, or even the motivation for this talk, if you want, is that many ML algorithms can be thought of as machine learning workflows. A good example that we have implemented on the back end right now is the random forest algorithm, the random decision forest. So in fact, all that really is a workflow around another machine learning algorithm, which is the algorithm that learns the individual trees. And all we're doing is basically configuring the parameters of a bunch of different trees automatically, learning this selection of trees, and then composing those trees into a single individual model. Everything outside of the tree learning is pretty trivial from a mathematical point of view. You can easily compose the tree learning algorithm into the random forest algorithm without very much computational heavy lifting. And so a lot of machine algorithms share this aspect of random forest, in that they're composable from other more basic machine learning algorithms. And so in a lot of these algorithms that I'm talking about, machine learning operations are the primitives in the algorithm. So making a model is something that will happen in a loop. For example, in the random forest algorithm, making a prediction is a primitive for a lot of machine learning algorithms, where you have to you learn a model, and then you actually make predictions on the training data, and then you go back and you fix your model based on the predictions that it just made. So you model and predict in a loop until you get predictions that you like. Again, the point here is that you're making the model and you're making the prediction in a loop. These are kind of basic machine learning operations that compose the algorithm itself. And evaluation, obviously, is another thing that can be thought of as a single atomic step in a lot of these machine learning meta algorithms that we're going to talk about. And so if you have an algorithm like that, like ensembles, for example, you could implement that algorithm in WhizzML. And again, why would you want to do that? Well, first of all, you reap the advantages of having our backend execute for you. So again, you get scale for free. You free up your own machine to do other things. You don't have to worry about storing the data or doing complex transformations. All those can be done by us on our backend on multiple machines and multiple cores and so on and so forth. And then once you've implemented an algorithm like this in WhizzML, it's essentially language agnostic. So any language from which you can make an HTTP post request, from any of those languages, you can call on our backend to execute that script at any time and pull down the results using the same sort of post request. So you can always tell BigML to run the algorithm. You can always get the results out from BigML using any programming language. And so this is kind of the benefit of one of the other benefits of this remote execution is that because it's not happening on your machine, it's not tied to a particular language. It's only tied to your ability to access the BigML backend. So let's look at one of these in detail. One of these machine learning meta algorithms I'm talking about. So an example is kind of a vanilla basic version of best first feature selection. And what does this algorithm look like? Basically, all we're trying to do is you've got a data set. It's got a whole bunch of features. You want to select the top n features because you want your models to go faster or be more simple. So instead of 10 features, you're going to try to model with only 3. And so a simple way to do this is you start with a set of features used so far. We'll call that set capital S, and we split our training data. We'll split our data into training and test sets. So you obviously don't want to test on your training data and vice versa, and so instead we're going to split the data and we're going to train on the training data and we're going to test on the testing data. We're going to iterate over and over again. We're going to iterate choosing a feature each time. So we start with our empty set, and then we choose a single feature. We move that feature into our empty set. Now it has a single feature in it, and then we'll just greedily select the next feature that improves the model as much as possible. So again, you can see in each of these iterations, we're doing all 3 things that we talked about before. We're going to model each of the features in turn. We're going to do an evaluation on the test set that allows us, or we're going to do predictions on the test set, and then we're going to evaluate those predictions. That will allow us to pick the best feature, and then we're going to iterate this whole process. So we have many, many models that we're learning, many, many evaluations that we're doing. Again, this is something that would be incredibly laborious in the UI, especially if you have thousands of features to go through at each iteration. And WhizzML is going to allow us to do that programmatically. That's the big reason we're going to do programmatic machine learning here instead of relying on a UI. And you see at the bottom there, we have a URL that tells us that gives us an address for this example if you want to go out and clone it and have it in your own UI to play with. So let's look at a WhizzML implementation of best first feature selection. So the first thing we're going to do is construct a bunch of models. Remember, we start out with an empty set. We start out with no features in our feature subset, and we want to be able to add the best next feature to the subset. So what are we going to do? We have the list of features that's already been selected. This starts out as the empty set, and then we have a list of potential features that we could possibly add. And what are we going to do? We're going to try in turn each of those potential features, add them into the list of selected features, and then make a model based on that subset, the currently selected features plus one of the potential features at each iteration. And so at the top, you can see we're using the let form again to do bindings to local variables here. So here we're going to make kind of a generic model request that has our data set ID mapped to the data set key and the objective field mapped to the objective field key here. And then we're going to define a function using this keyword lambda which we've seen in a previous lecture, I believe. And we're going to say this function lambda takes a field ID, and all it does is it associates the key input fields in our original model request with that field ID concatenated onto all of the selected fields. So given a field ID, this will compose a new model request that has as the input fields all of our selected fields so far, again, which start out as empty, plus the field we pass in. And then we're going to use this function map to do that over all possible potential features to add. So essentially, what are we doing here? We're making a list of model requests, and each model request is going to have slightly different input fields. And each model request will have input fields that are the selected input fields so far, and then one of the potential fields added on. So all of the model requests that we make look very similar. They're only different in this aspect where they have just slightly different input fields because we're trying each of the input fields in turn. And so all requests here is going to be a list of model requests, and then we just use this function create and wait star, which is super useful. All that's going to do is going to create a bunch of models. The first argument is the type of resource that you want to create, and it's going to do it for all these request maps that we passed in. So all of the requests are going to get executed in parallel, and create and wait star means we're going to block until all of those requests are completed. So again, you already can kind of see the payoff here in terms of efficiency. Rather than having to create all of these model requests by hand in the UI, all you have to do is use this create and wait star function, and you can create potentially thousands of resources with a single line of code. Then the next thing we have to do once we have all of these models is we have to conduct evaluations over all the models, because we want to know which one was best. Remember, each of the models we created in the last slide has slightly different input fields. We've tried each of our potential features and added them to our list of input fields one by one, and now we want to create a set of evaluations over those models. So we define a function here that takes a test dataset ID, the list of potential fields that we just tried, and the model IDs corresponding to those potential fields. And the function itself looks pretty similar to the last function we saw. We have this let binding in which we're going to make a generic evaluation request that just contains the test dataset ID. And then we create another function that will take in the model ID and associate to that request the model ID. And so again, we're going to map over those model IDs to get a list of evaluation requests, and each one is going to have a different model ID. Then we use create and wait star again to fetch all of our evaluation maps. So remember, this fetch pulls the metadata for the resource down from BigML. So we're going to wait for all of the evaluations to complete, and then we're going to fetch all of the evaluations. That's what this map is doing, is again mapping over all of those evaluation IDs. And once we have them, we're going to define a little function here that will pull out the average phi using getIn from the previous lecture, that will pull out the average phi from each of those evaluations. So now we have a list of values, which is the average phi from each of the evaluations we conducted. And then finally, we're going to use this function makeMap, which we haven't talked about. It takes a list of keys and a list of values, and it maps a key to each value. And so in this case, our keys are going to be the IDs of our potential feature, 00000 here, or the first feature here. And we're going to map each of those keys, the potential features, to the result of the evaluation, the average phi from the evaluation that we pulled out in the previous line. So basically what this is a map of, I added this feature and I got a solution that was this good. I added this feature and I got a solution that was this good, and so on and so forth. And then all the last couple of things we have to do here are pull out the max value from that map and then choose the best feature based on the value it's been given in the map. And so that's basically the main work of the algorithm. We have to make these models, one for each feature, and then we have to conduct evaluations over those models. Again, one evaluation per each model that we just learned. And so the main loop of the algorithm is pretty simple once you have those two steps defined. Here's the main loop of the algorithm: select features. All it takes is a data set ID and the number of features you want to pull out. I'm using one of the built-in functions, dataset get objective ID, to get the default objective for the dataset. I've defined a function, a helper function elsewhere in the script called default inputs that gets all of the default input IDs. And then we'll split the data into training and test data, as we do so many times in scripts like this, and in the same way we did in the last session. And then, as I said before, I'm going to start with an empty set of selected features, and then my potential features are going to be all of the possible input features in the dataset that I define above. And then finally, we're going to loop as long as either of these conditions is not true. So we want to make sure that we don't go over n features. That's the number of features that we wanted to select. That was the input parameter to the script. And also, if we run out of features, we need to stop as well, because obviously there are no more features to add. And so what we're saying here is that if either of these things are true, if we've gone over our target number of features, or if our potential new features is empty, then we're going to return the list of selected features. And I've got this function feature names that I've defined. All it does is pull the actual text name for the feature rather than the ID, just so the output is a little more meaningful. But all this line does is return the features that we've selected up until this point. If neither of the conditions are met, if we're not to our target number of features yet, and we still have features left that we could select, we do those two steps that we defined above. We make the models for each potential feature, and then we use the function select feature to take that list of models, conduct a series of evaluations, and compare those evaluations so that the best next feature is chosen. And then once we've selected a new feature, we can add that feature to the list of our selected features. That's what cons does. It adds an element to a list. And then we're going to filter out that feature from our list of potential features, because we can there's no point in selecting it again. So pretty simple as code goes. And part of the reason that the code was reasonably simple, short, terse, is because all of the machine learning operations, again, are one-liners in BigML. So you don't have to do anything special, to load the data, for example, because the data set is already a primitive operation in BigML. Creating models is a single line of code, and so on and so forth. So what are some other interesting workflows we might be able to implement in WhizzML? One example is a kind of a classic machine learning algorithm called stacked generalization. And basically the idea behind this is you improve predictions by using models themselves as the input features. So basically we're going to create a training and a test set, and then on the training set we're going to create, or a training set and a holdout set rather, and then on the training set we're going to create n different models, where each of those is going to be slightly different somehow than the other one. So for example, we can do single tree versus ensemble versus logistic regression. That would give us 3 models, and those could be our 3 models. But it won't do us any good to create 3 of the same ensemble, because then we'll just get features that are identical. Then we'll make predictions for those models onto the holdout set that we defined before, and then we'll train a meta model that uses the predictions as features in the model at the next level. So basically, we create a bunch of models. Those models make predictions. We use those predictions as features, and then create another model that tries to kind of trade off those features against one another, and maybe for a given instance, it's able to choose which one of those models is the best predictor for that particular instance. So rather than choosing one of these things, we're either going to choose logistic regression or or single tree or ensemble. Instead of choosing one of those, as we did in previous examples, we're going to just train them all and let machine learning decide which one is the best for a given data instance. Another nice example here is randomized parameter optimization. So what's our objective here? We want to find the best set of parameters for a machine learning algorithm. One kind of simple but usually functional idea for finding a good set of parameters for an algorithm is to just try a whole bunch of them. Just randomize the values of all the parameters, do this a whole bunch of times, train hundreds and hundreds of models, and then do tenfold cross-validation with each set of parameters that you've chosen. And so in this way, you're able to kind of basically just essentially throw stuff at the wall until something sticks, and finally you just choose the best random candidate that you found according to your cross validations. And nice thing about this, of course, is that you can do it for as long as you want. So if you have the time and resources to try thousands of different random candidates for your model parameters, you can do that in BigML and in parallel if you want. And BigML will churn and churn away. And the more you try, the more likely you are to get something that works better than everything you've tried so far. But also, if you only have the time or resources to try one or two random sets of parameters, you can do that as well. The algorithm, it obviously won't give you as good of a solution, but it's nice to have an anytime solution in that sense, where regardless of how many random candidates you try, you're bound to get at least one that will give you an answer, provided you try at least one. And then if we want to be a little more clever about parameter selection, we can do this thing we call Smackdown here. This is a WhizzML implementation of the SMAC algorithm, which you can look up in the academic literature. And basically, instead of just trying random sets of parameters, we're going to let the previous evaluations of parameters guide our search for the next parameters. So essentially what we're going to do is we're going to start out by generating some random sets of parameters as before. We'll do cross-validation with those parameters to evaluate how good they were on our data. And then we'll actually learn a model on the parameter sets to predict performance for parameter values. So there's no reason that we can't treat the performance of a machine learning algorithm as data that can be modeled in and of itself. So we'll try all these random parameter sets. We'll evaluate them all, and then we'll learn a model that will predict how good a given set of parameters might possibly be. So for example, it might turn out that when parameter 1 of the algorithm is in some range, things go really well, and when parameter 1 is out of that range, things go really poorly. So this is something that machine learning can find out, right? Parameter 1 is just a feature, and performs really poorly is just an objective. Or we use modeling to decide which parameters to evaluate next. So the first time we just choose at random. The second time we use the model to choose. So we propose a bunch of random parameter sets to evaluate, and the model that we learned on the last iteration says this 10% of those parameters, for example, those are the ones you should try because those are the ones that are most promising to evaluate, that are most likely to give you some kind of performance improvement. And again, this is another anytime algorithm. You can just do it until you're bored of trying, or until you meet some sort of minimum performance threshold. And this is something that we're going to try to bring to the UI on kind of a more first-class basis than your average WhizzML script. So this should be coming soon to the gallery, to the UI, somewhere in the very near term. And then the last one I'm going to talk about here before I get into another quick example is boosting. So boosting is kind of a famous machine learning algorithm that's gotten a lot of good press lately because there's been some nice open source packages that have done really good things around boosting. All boosting algorithms have the same flavor. Basically, we're going to iteratively model the data set. So each iteration of the algorithm is going to be trained on the mistakes of previous iterations. Another way to say that is that the objective function is going to change based on the previous iteration of the algorithm. So if you made a mistake on some instance in a previous iteration of the algorithm, we're going to try harder to get that instance right on the next iteration. And then the final model, the final gradient boosted model, is going to be a summation over all the iterations that you trained for. And there's lots of variations on this theme. One is Eta boost, that's kind of the classic one, but there's also logit boost and martingale boosting, which are new sorts of boosting that kind of remedy some of the weaknesses of Eta boost. And then there's also gradient tree boosting, and we're going to take a look at just a tiny sliver of a gradient boosting implementation in a moment. So let's do these. Let's take a look at these last two examples. The first one is going to be stack generalization, which we mentioned before. Remember, that's the algorithm where we're going to train a bunch of models and then use a model to decide which of those models is the most robust, to decide which model or models to base the final predictions on. And so here we've got a function make stack that's going to do the work of making the stack of models, and essentially we're going to just take the steps that we outlined before. So here we're going to split the data set at the very beginning, as we do in so many of these algorithms, and then on the next line down, we've got this function called create stack models. We assume that's defined elsewhere, which is going to create a list of models, again with some heterogeneity between them, as our constituent models. And then after that, we create predictions on the holdout set, and then we learn a meta model. You see here meta ID. It's going to create and weight model on that data set that now has the predictions from the constituent models appended to it. And then we check for success on the meta model, and then we return a JSON friendly kind of map here that tells us the constituent models, the meta model, and whether or not the training was successful or not. So again, kind of a reasonably complex idea. We can express that pretty tersely here with WhizzML. The exceptions here are the create stack models, which we haven't defined, but which is, it could be anything really. It could be an ensemble and a tree. It could be an ensemble and logistic regression. It could be several different types of ensembles. And then this create stack predictions, which will make predictions from each of the models on the holdout set. Here's a piece of the latter two functions. This is the one that creates a prediction using the stack. So basically, this is going to create the constituent. This is going to take the constituent models. It's going to use this map function again to create a prediction with each of the constituent models. Then it's going to grab once the predictions are complete. It's going to grab the prediction. It's going to grab the prediction key from the prediction metadata, and then it's going to use those predictions to make new input for the meta model. So here we have this meta input. We're going to make a map containing the new features and values for the meta model, and then we're going to pass that into our create prediction function using the meta model as the predictor, and as the input data, the meta input, which is the predictions from our constituent models. Yep. So again, pretty simple. Predicting with one of these stack generalization models. You just get your constituent predictions. You make new prediction data based on those constituent predictions, and then you pass it into create prediction to create your new meta prediction. Just a few other auxiliary functions here to make a batch prediction for a given data set and model ID. Again, these are things that you need to compose the rest of the script, but we won't talk too much about these here. Again, these are just simple utility functions. Here we're getting the ID of the data set that comes out of the batch prediction resource. And then at the bottom here, we're just getting the input fields for a model. So these are things you often have to define in your WhizzML scripts just to make them look a little more clean. And if you want, I think we have the URL for the script towards the end here. If you want to look at how those auxiliary functions are used in the script, you can go to the URL and clone this for yourself. Okay, so finally, just taking one more look at a complex workflow in that can be implemented in WhizzML, and we do have an implementation of this also. This is going to be a little bit of gradient boosting. So our last workflow here, gradient boosting, what does it look like? This is easily the most complex thing we're going to talk about today, and so we're just going to talk about a little piece of it. So how does it work? Remember, the boosting algorithms work by trying to correct the mistakes of the previous iterations of the algorithm. So the first thing we have is we have some currently predicted class probabilities, and so for each instance in our training data, we have the probability of each class according to our model as it stands right now. At the beginning, of course, it's just going to be the uniform distribution. Each class is as likely as any other before we've learned anything. And then all we want to do is, given those probabilities, which represent our model up until this point and the mistakes that it might be making, compute a gradient step that will push those probabilities in the direction of correctness. So just try to push the probabilities to be a little more correct than they are right now. And the way that we'll represent this gradient step is by learning regression trees. So we'll learn a regression tree to represent the step, to represent the gradient step that pushes the probabilities in the right direction. We'll make a prediction with each tree. We'll sum that into all of our predictions so far. And then we'll apply some mathematics to make those sums into class probabilities for each point. And now we have class probabilities again, so we can just loop around and do the whole thing again. For a full implementation of gradient boosting, it's pretty terse, but unless you have experience with WhizzML, it's probably difficult to read. So best to go through some of the other examples before you take a look at this. But once you do, it provides a pretty good example of kind of a lot of the things that are possible with the language. Okay, so what does this look like in WhizzML? As with these other algorithms, a lot of the pieces of the algorithm are these machine learning primitives that we were talking about before, constructing the models, the regression trees that represent each gradient step, and also making the predictions with each of the regression trees. But some of these are kind of not natural machine learning operations. For example, summing all of the gradient steps is something that's not a machine learning operation. It's just basic arithmetic. Computing the softmax probabilities, computing probabilities given the sums of scores, again, isn't a machine learning thing. It's just doing some mathematics. Computing the gradients, similarly, is just math. It's not machine learning in particular. Again, we don't want to do those things locally. We don't want to have to bring our whole data set down into local memory to do these simple mathematical operations over each point. We'd like to do it on BigML's infrastructure. Can we do that? And of course, I wouldn't be saying it out loud if we couldn't. And so let's look at one of those things. So let's look at computing the gradient. Computing the gradient turns out to be pretty simple. All the gradient is the true class of the example. We're calling it y here, minus the currently predicted probability. So if the true class, for example, is 1, and the currently predicted probability of that class is 0, then the gradient is going to be 1. If the true class is 1 and the currently predicted probability is 1, then the gradient is going to be 0 because everything's good. If they agree, everything's good. If the true class is 1, the probability is 1. We have a 0 gradient. We don't need to push the probabilities in any direction because we're already correct. If they're different, if the true class is 1 and the probability is 0, or vice versa, if the true class is 0 and the probability is 1, then we do have some work to do. We have to push the probabilities in the direction of correctness. So this is a good definition for our gradient, and also very simple, right? All we have to do is subtract one column in the data set, the true class, minus and subtract that, or subtract from that the probability for that class. So let's look at what this looks like. In practice, if the problem is non-binary, if it's instead a 3-class problem or a 4-class problem, we end up with a class matrix. So here we have the original features of our data set in the first 2 columns. This is kind of an imagined example. And then we have the class matrix. So this is a 3-class problem, and it's going to have a 1 in the column where there's the true class for that example, and it's going to have a 0 in both of the columns that aren't the true class. And then the last three columns here are the current probabilities that the model is predicting. So in this case, the model thinks that it's 60% chance that this example is class 1, a 30% chance that it's class 2, and 10% chance that it's class 3. And you can see that that agrees somewhat with our class matrix over here. So it's doing pretty well on this example. Other examples, for example, this middle example, it's not doing quite as well. It thinks there's a 40% chance it's class 1, 40% chance it's class 2, and a 20% chance it's class 3. And in fact, it is class 2 in the middle here. So it's only assigning the correct class a probability of 40%. So this is what the basic structure of the data looks like at any given iteration of the algorithm. You have the class matrix, which gives you the true class for each of these points, and you have the currently predicted probabilities for each of the points. And so what we want to do in this little tiny slice of the algorithm that we're looking at is compute the gradients. And all we're going to do is subtract the first column of the class matrix here from the first column of the currently predicted probabilities over here. And similarly, the second column from the second column, and the third column from the third column. And when you do that, you get your set of gradients for the algorithm, which again are just the differences between those two columns. And so how do we compute those columns? We want to generate those columns from scratch. And what we're going to do is we're going to use flatline. What's flatline? Flatline is a data manipulation language. We use it to transform data sets in BigML. You can see the user manual if you've never used it. But a really important aspect of WhizzML is that flatline is a first-class citizen of it. And so you can do flatline transformations in WhizzML without very much hassle. And the nice thing about this, again, is that instead of doing data transformation on your end inside of your machine where you have these things to worry about like scale and parallelism and so on and so forth, you can do any sort of transformation on your data in the cloud using our computers instead of yours. And so we want to create new features for our data set in flatline. And as I mentioned, each of these new features is just one of those columns in the data set. Here we're calling it actual, the true class of the point, minus the column we're going to call predicted, which is the probability of that class as given by our model. So just the difference that we were looking at in the example, the difference between those two columns. Of course, if we have n classes, in this case, in our example, we have 3 classes. We have to do that 3 times. So in general, if we have n classes, we have n gradient columns we need to construct. We're going to do n subtractions. And so here comes the WhizzML function that allows you to do that. There's a few functions defined here that I've defined elsewhere in the script, like grad names gets the names of all the gradient columns. Softmax names gets the names of all the columns with the probabilities in it. But basically, aside from that, it's pretty simple. We have this FEXP, which is going to be the function that constructs those flatline expressions that will compute the difference. And basically, it's going to take an index. So it's going to take an index from 0 to n, where we had n classes as before. And then it's going to get the name of the actual column, the name of the column with the true class in it. And then it's also going to get the name of the predicted probability for that class. And then it uses this WhizzML function flatline just to take the difference between those two columns. And remember, this is a function that we're defining here using the lambda keyword that takes as its argument an index. And so what do we have to do? We have to map this function over all of the indexes, which here is going to be the number of classes. So we're using range to construct a list, 0, 1, 2, 3, ... all the way up to the number of classes. And then we're going to call this function on each element of that list. And that's going to produce a bunch of flatline expressions, each one of which is going to take the difference between one column, the column for the true value for that class, and the column for the predicted probability of that class according to the model. And then it's going to use this makeFields function, which is something I defined elsewhere in the script, to make a new set of columns with the given set of names based on those flatline expressions. And then we add those fields to the data set, and we're all set. So again, the nice thing about this, one of the nice things about this is that we haven't had to touch the data at all here. We've computed this function that generates these flatline expressions, and then we just call BigML and say, add these to my data set. And so we do no explicit iterating over the data, explicit or implicit iterating over the data in this function. We just compose essentially a fancy API call to BigML and let BigML do the iterating over the data for us. Okay, so with that, a lot of new information in there. Obviously, a lot of excuses to kind of run around and play with WhizzML if you want to. What have we learned? Especially with that last gradient boosting example, and especially if you go and look in our examples that we have online, it really shows that if you've got one of these algorithms, it doesn't matter how complex it is, these machine learning meta algorithms, you're usually able to implement that in WhizzML without too much trouble. At the end there, we talked a little bit about the power of WhizzML and flatline. The reason that WhizzML plus flatline is so powerful is because it turns almost any data manipulation task into a BigML API call, which means you can do basically any sort of data manipulation from WhizzML, which again means that you can do anything you want to your data inside of the BigML infrastructure. And finally, the last thing we kind of try to push hard with is that once you've implemented something with WhizzML, it becomes both language agnostic. So again, you can access that script from any language from which you can make a HTTP request, and also it becomes architecture agnostic. So you implement this algorithm one time, and regardless of what sort of subscription level you have at BigML, or maybe someday your company or organization decides to do a private deployment of BigML behind its own cloud servers, WhizzML automatically does all of that scaling for you. So if you have hundreds of machines, if you have a single machine, if you have the basic account, if you have like the Super Pro Gold Plus account where you can run a billion things at a time, WhizzML automatically scales your algorithm, or the infrastructure will automatically scale execution of your WhizzML algorithm according to your subscription level, to the resources you have access to. So you never have to worry about, basically you never have to worry about implementing it in another language, because you can access it from any language, and you also never have to worry about architecture again, because you can customize the architecture that you have available to you under BigML, and all your algorithms will kind of scale automatically.